All right, 4.6, model direct variation. So, two variables, x and y, show direct variation if y is equal to ax and a is not equal to 0. So direct variation is the key there. The constant of variation is a. So from this equation, a is the constant of variation. And we say that y varies directly with x. So if anything is in this equation other than y is equal to some number times x, so if there's like a +2 or a -500 or whatever, it's not direct variation. It has to look just like this to be direct variation. So, example, if we had -x plus y is equal to 1, and we want to decide if it's direct variation. Thanks. I have a weird sneeze, I know. Then we have to get y by itself. Okay, that's always the first thing, get y by itself. So I'm going to add x to both sides. So I have y is equal to x plus 1. But it needs to be in the form y is equal to ax, and a can be 1, but because this plus 1 is here, it is not direct variation. And a lot of times I'll just use dv for direct variation just to shorten it because I don't want to write it all out. And if it was direct variation, I would just write dv to show like yes or no it is or is not. If we had something like 2x plus y is equal to 0, I need to again get y by itself, so I'm going to subtract 2x. So I have y is equal to -2x, and there was just a 0 there to begin with, so I don't need to write it. So now y is equal to ax. A is now -2. Okay, there's nothing after it, so this is direct variation. Let's see, another example. We had something like 4x minus 5y is equal to 0. How would I go about getting y by itself in this one? Yep, minus 4x. So I have -5y is equal to -4x. The 0 is just gone now. Now what do I have to do? Divide by -5. So y is equal to -4 divided by -5. Obviously, I can't reduce that, but I can get rid of the 2 negative signs, so it becomes positive. So 4/5 times x. And so then this is in the form y is equal to ax. And so this one is direct variation. And something I forgot to actually write up here, I kind of mentioned it, but a in this previous one was equal to -2. So a in this one would be equal to what?
A equals 4/5.
Yep, 4/5. So it's just the number that's in front of x is always going to be a. For some reason, this concept of direct variation, a lot of times people get really confused about it. And I mean, I'm one of the people that got really confused about it when it was taught to me. So, like, if you're like, oh, this seems easy, and then you go to do it and you're like, I'm really confused, that's normal. So, let's see. Trying to figure out. All right, let's see. I'm going to do this note thing and then. So, properties of graphs of direct variation equations. So basically, we can take our direct variation equation that's here and we can graph it just like we were graphing the y equals mx plus b. The difference with this is that b is equal to 0. So we don't have our y-intercept. Well, I say we don't have a y-intercept. Our y-intercept is at 0, so it's on the origin. So let's see. The graph of a, and I'm just going to write dv for direct variation equation, is a line through the origin, so through the point 0, 0. And the slope of the graph of y is equal to ax is a. So I'll show what two different graphs of this look like. So basically, if a is positive, then our line goes through, well, that's really wavy. Goes through the origin like that. If a is negative, it goes the other way. And goes down like that. Oh, sorry. That's like not even on the screen. So the only difference in graphing these from what we did the other day is the fact that your y-intercept is always 0 for these ones. And then your slope is just whatever the a value is. So just how you were finding m before, you do the same thing. So let's see. I'm going to do like two easier examples that are already set up for you, and then I pretty much have to go, but we'll pick it up tomorrow. But I might give you a couple to go ahead and try and just see how you're understanding it so far, and then we can pick it up tomorrow. So from the examples, I'm going to do number 12. Y is equal to 3x. So I'm going to set up a graph. So, again, my y-intercept, so I'm going to still do this like I normally would. M is equal to 3, okay, or you can call it A if you want to, but M is slope, so I'm just going to call it M. B is, there's nothing there, so it's 0. So I have my point at the origin. That's always the first point that I plot as my y-intercept. What does that slope of 3 mean that I do?
3, right 1.
Yep, up 3, right 1. So 1, 2, 3, right 1. Up 1, 2, 3, right 1. And then we just connect the dots. Let's see. I'm going to do one more, and then I'll give you a couple that you can work on while I'm gone. So then number 16, y is equal to 1/2 x. So I'm going to set up the graph. So my slope is what?
1/2.
1/2, and y-intercept is
0.
0. So my first point goes on the origin, And then what does that slope tell me to do?
Up one, right two.
Up 1, right 2, and then up 1, right 2, and then just, whoa, that's not even connected. No, close enough. Does that kind of make sense?
Mm-hmm.
All right. So 3 through 8 are like the first set of examples that I did. I just did the guided practice examples. So I'm going to give you, and I know we've gone through it quick, so don't worry if you're like, I'm really confused. Tomorrow we can go over it some more. 3, 5, 7. And then as far as graphing, let's go ahead and do 11, 13, and 15. And then we'll pick that up tomorrow.